Now, the idea of the critical point is that it is pre-calculated as part of the flight planning process. Then, as the aircraft passes over the last point of diversion before the oceanic leg, the actual time of arrival is noted. The pre-planned time to the critical point is extracted from the flight plan and added to the actual time of arrival over the last waypoint. This takes all the decision-making out of in-flight emergencies. If one should occur, there is no frantic searching through charts or rapid calculation in the air. The decision is a simple one. If the time is less than 112.5 minutes after the last waypoint, we turn back. If it is more, we go on. We do not want to complicate this decision by having different critical points for different situations with different ETAs. Because the difference between the 2 points is usually quite small, we always take the one engine out situation. This covers the worst case, so this is the calculation we use. The all engines time to the critical point is usually very similar whether we take the all engines or the one engine out point. However, if we use the reduced TAS after the critical point, the time to the alternate airfield will obviously increase. The distance to the one engine out critical point X was 974 nautical miles. With a total distance d of 2,050 nautical miles, the distance onwards from the one engine out critical point is 1,076 nautical miles. O, the reduced ground speed onwards, is 370 knots. And H, the reduced ground speed home, is 335 knots. As before, if you get your calculator or nav computer out, you find that the time onwards, that is, 1,076 nautical miles at 370 knots, comes to 174.5 minutes. And the time home is 974 nautical miles at a ground speed of 335 knots, which also comes to 174.5 minutes. The time we calculated using the all engine speeds after the critical point was 137.5 minutes. This is shorter by 37 minutes. Sometimes you are given wind velocity and track instead of component, and you have to calculate O and H yourself. Here is an example. The track between A and B is 030 degrees true, and the distance is 500 nautical miles. The aircraft has a true airspeed of 180 knots. The forecast wind all the way along the route is 35 knots from 090 true. What is the distance and time to the PET? We first need to find O. Plot the wind velocity of 090 at 35 knots on your navigation computer. Rotate the inner scale to put the outbound track of 030 against the 12 o'clock index, and move the speed scale to put 180 knots TAS under the centre circle. You can see that this gives an initial 11 degrees of port drift. You now need to balance the drift in order to get an accurate ground speed. Rotate the scale until the heading reads 040 degrees, with 10 degrees of port drift. This gives you a track of 030. This gives O as 160 knots. Now we find H. If the outbound track is 030, the homebound one must be the reciprocal 210 degrees true. Rotate the inner scale to put the homebound track of 210 against the 12 o'clock index, still keeping 180 knots TAS under the centre circle. You can see that this gives an initial 9 degrees of starboard drift. Balancing the drift again, rotate the scale until the heading reads 200 degrees, with 10 degrees of starboard drift. This gives you a track of 210 and gives H as 195 knots. The TAS was 180 knots. Notice that O was 160, giving a 20 knots headwind component. H is 195, giving you a 15-knot tailwind. This becomes obvious when we look at the triangle of velocities. The outbound track is 030. Plot in the wind, 090 at 35, downwind. With a pair of compasses, draw arcs corresponding to 180 knots of TAS, and draw in the lines corresponding to the air vectors. This is O, with its heading of 040, and this is H, with its heading of 200. You can see that the geometry of the triangle of velocities does not always give a tailwind component of the same value as the headwind reversed. You have to solve the triangles with a navigation computer in both directions. If you make approximations of the wind component using rule of thumb methods, or assume that the tailwind component is the headwind component reversed, you may well get the wrong answer. Let us summarize what we have covered. Point of equal time, or critical point, can be found from the formula x equals d times h over O plus h. This is the starting point for all point of equal time questions. Some calculations assume a constant wind component all along the route. However, the forecast wind may well vary over the flight. This is not a problem, because the equation deals with this situation as long as the wind change point is assumed to be the critical point. Forecast wind along a route can be split into two halves, and then averaged over each half. Emergency situations may also result in a loss of altitude and power, and consequently a reduction in TAS. The same equation also covers this case, as long as the reduced TAS is used in the calculation. However, if a reduced TAS is used to calculate the position of the critical point, the time to the critical point is still based on the all-engines ground speed. Unless there is a strong wind component, there is usually little difference between the position of the one-engine-out critical point and the all-engines critical point. In order to keep the decisions simple, we use just one point of equal time. This is always the one-engine-out case. And finally, if you are given wind velocity and track instead of component, and you have to calculate O and H yourself, you have to solve the triangles with a navigation computer in both directions.